The prisoner's dilemma, we were talking about this. First of all, why study? This game is really, really simple, right? I mean, you get to make one choice. Your choice is stay silent, meaning cooperate with your buddy, or blabber on your buddy and betray him, and then you get the payoff. And how hard is it to compute the utilities for the prisoner's dilemma? They're given to you in these numbers, right? So doing utility theory is pretty darn easy. What should you do? Well, pick the number you want. It's a very simple game. Why is this game interesting at all? Essentially, the reason we're looking at prisoner's dilemma is this. It's simple. We're doing it on purpose because cooperation, it turns out, is kind of hard. And so obviously if you're going to debug something hard like the principle of intelligently cooperating, you're going to start with the simplest problem you possibly can so you can debug it. Same thing we were just talking about. Yeah. That's why we're investigating a really simple problem, is because, hey, if we can reason about this, then maybe we can move on to the next harder thing. So let's reason about the prisoner's dilemma. The really interesting thing about prisoner's dilemma is the fact that maximizing your utility doesn't seem to give you the best answer. So let's suppose you are A, and your partner who is complicit in crime is B. Okay, what is the best decision for you? Your two choices are stay silent or betray. And your utility is the one on the underside of the slash. If you stay silent, you're either going to get a -1 or a -3. If you betray, you're going to get a 0 or a -2. Basically, your utility is better in both cases if you betray. So think about this. What are the odds that your partner's going to stay silent? What if they're 50-50? Well, then your utility is going to be 50% times 0 plus 50% times -2, which is going to be a -1 for betray. And it's going to be 50% times -1 plus 50% times -3, which is going to be -2. And therefore it's better to betray. Okay, what if the odds are, what if you know your partner is the most loyal man ever? He's definitely going to stay silent. Do you stay silent or betray? Yeah, it's always in your personal best interest to betray in this game. Even if you know your partner is totally loyal, you should still stab him in the back because, hey, then you can get 0, and 0 is better than -1. According to this principle where you maximize your own personal utility, right? Okay, and yet, having considered what maximizing your utility does, is that the best answer? How do you really play this game? Yeah, that's the mini-max principle right there, is if you're assuming that your opponent is maximizing their utility and then you maximize your utility with that in mind, that's mini-max. That's how mini-max was invented. Well, okay, so we see the problem, but notice, imagine that this happens a lot, you and your buddies. So we're going to switch now from the prisoner's dilemma to what's called the iterated prisoner's dilemma. Imagine we now play this game not once, but every week. If you're doing it once, obviously betraying is the right answer. And in fact, betraying is the right answer if you're going to say that the payoff of the universe is determined only by how much you benefit from it. Now, I think that's a very selfish and terrible thing to say, but you know, if that were the definition of best, you should betray. That's the answer. And so it's not that utility theory is wrong, it's that it's improperly applied. Now we switch to the iterated prisoner's dilemma. Imagine you're going to do this over and over and over. Now, should you betray your buddy? A lot? You know how when you're eating at a restaurant and you're about to pay the tip, does it ever cross your mind, am I going to come back to this place? And is that wrong? It's game theory though, isn't it? Because you're thinking, if I'm going to come back, I want this waitress to think, you know, hey, this guy has left me a tip before. Whereas if you think this is the last time I'm coming here, because when I'm on vacation, do I tip as big? Well, hopefully I suppress that part of my mind, because some part of my conscience tells me that, I don't know. But basically what I'm thinking here is, the waitress is going to learn from how much I tip, right? Imagine if you betray your buddy 10 times in a row. Is your buddy going to stay silent? Not a chance. They're not going to be your buddy after 10 times in a row, I would assume. So because your actions affect what your partner does, think about it. What if you have this little camaraderie and you keep saying to each other, let's always stay silent, and you actually follow it? What happens? After 1,000 iterations, you have a combined utility of negative 1,000 from you and negative 1,000 from your partner, for a total of negative 2,000 cost has been paid. And now what happens if you two just stab each other in the back all the time because your friendship just doesn't last? Well, now you've paid negative 2,000, your partner's paid has paid 2,000, and now that's a total cost of negative 4,000, which is, or cost of 4,000, a utility of negative 4,000, which is obviously worse. In fact, it's twice as bad as if you had just cooperated. So kind of we all agree the right answer is you should cooperate. Yeah? And thus the problem with utility theory, thus the perception in game theory that utility theory fails when applied to cooperative games. And that's interesting. So then we're left with the question, what is the answer? How do you determine what is intelligent to do in a cooperative game? And we could just say, we'll always cooperate, but that's not necessarily true. What if we change the numbers? What if you change the game? What if we made it more complicated? What if there were different types of cooperation? How do we be intelligent in an arbitrarily complex but not zero-sum game? Isn't that an interesting and fun problem? Okay, so there was a guy named Axelrod, Robert Axelrod, who decided to try this problem. He went with Prisoner's Dilemma because it's this very standard game theory problem they've been studying. And so he created a competition. And he invited a bunch of people from different universities to submit code that would play the iterated Prisoner's Dilemma. And the idea is he'd run a simulator on his machine, picking random players and battling them against each other. And whoever got the best total utility in the end was the winner. And they would have agents battle each other, not unlike what we're going to do at the end of this class, except not with Prisoner's Dilemma. We're going to have a much cooler game than that. And basically, he ran this tournament for years. And people kept submitting different strategies and different bits of code to this, to play the Prisoner's Dilemma. So just to consider this, let's consider a few different strategies. There's a strategy called always cooperate. What do you think that does? It always cooperates. It basically, it always stays silent. There's another strategy called always defect. What do you suppose defecting is? That's where you rat on your buddy, you stab him in the back, you betray. We can call it always betray if that's easier to remember. Betray. Always betray basically says you always betray your partner. And okay, there's another one called never forgive. This one basically says cooperate, cooperate, cooperate until your partner stabs you in the back one time, and then you stab him in the back forever. See how this one's kind of a pretty good strategy? Maybe? Okay. Then there's a random strategy, and these are just the really simple ones I can think of. You can imagine coming up with hundreds of these things, right? How do you think they do? Yeah, it depends on who they face. So imagine if you pit always cooperate against always cooperate. They're going to do darn well because they're always cooperating. And so, in fact, it turns out that as long as these two always battle each other, they're going to do as well as any other strategy. But this, it turns out, is not the optimal strategy. It's slightly more complex than you'd think it would be, because if you do an always cooperate against and always betray, what happens? Betray kicks his pants, and always cooperate loses, has to pay up. So it turns out always betray will totally stomp the tournament if those are the only players involved. But if you pit always betray against always betray, they sit there betraying each other, and so they don't maximize their overall utility, whereas always cooperates do. So who's better, always cooperate or always betray? It turns out always betray, you can't really take advantage of him, whereas always cooperate, you can. So if you have intelligent agents, always betray kind of seems to rise above, and always cooperate gets eaten alive. It's just too altruistic for this particular type of game. So in the rankings, I think Always Betray does better. It's been a decade since I read this book that actually documents it, so I could be mistaken. I apologize if I'm wrong, but I think that's the case. What do you suppose Never Forgive does? Well, interestingly, if you play Never Forgive against Always Cooperate, they sit there and cooperate with each other just fine, right? So Never Forgive gets the same benefits as Always Cooperate, but Never Forgive is not exploited by Always Betray. So if you play Always Betray against Never Forgive, well, Never Forgive gets abused one time, which isn't a huge deal, but then it turns around and plays an intelligent strategy. So it turns out that Never Forgive is clearly more intelligent than Always Betray or Always Cooperate because it handles both strategies fairly effectively. Random doesn't do so hot. I don't remember where it falls in the ranking. I'll just delete it so I can get rid of that. But you can see that some strategies are better than others, and Never Forgive is slightly more complicated, right? So we're starting to sense that there might be a degree of intelligence necessary to make a good decision in cooperative games, right? Well, there was another strategy titled Tit for Tat. Here's what it does. The first time it cooperates, meaning it's being kind of hopeful. It hopes that, hey, maybe things are going to work out. Maybe I can establish a good, trusting relationship with the other person. Thereafter, it does what he did last time. Meaning, if you cooperated last time, I'm going to cooperate this time. And if you stabbed me in the back last time, I'm stabbing you in the back this time. So let's suppose tit for tat plays tit for tat. So the same strategy is playing itself. You see how this creates perpetual cooperation, which is the goal, right? Well, imagine that, so at least tit for tat against itself does really well. Think about how it does against Never Forgive. It's cooperate forever, right? Because neither of them have any reason to be upset at each other. Think about how it does against Always Betray. Well, they always betray each other. But at least tit for tat isn't getting taken advantage of, except for once. So it doesn't do as well as Always Betray against Always Betray, but it does one notch worse than that, which is almost as good as can be done. And against Always Cooperate, it does darn well too. So here's the thing that came out of these tournaments. Turns out Axelrod ran this for a long time, and some people had started using machine learning to develop adaptive models that try and predict what the opponent is going to do and use those predictions to make good decisions. And yet, after a long period of time, the strategy that prevailed ended up being tit for tat. It always seemed to beat everything. It turns out it's a really good strategy for the prisoner's dilemma, and isn't that interesting? What implications does that have for the prisoner's dilemma? So it suggests that this is a near optimal strategy. We know something that turns out to be really good to do in this particular game, and can we from that derive a general purpose algorithm for making intelligent decisions in cooperative games? If we can, that's interesting and cool. The prisoner's dilemma is really interesting because there's a whole lot of analogs for all kinds of real-world situations. They've studied this in politics. Can you think of any situations in politics where life is like a prisoner's dilemma? Yeah, Congress, hey, I'll vote for your bill that I don't like if you vote for my bill that I don't like. There's cooperation even though there's competition. Don't you agree?